Section 3.4 is all about techniques in graphing, trying to use pictures of graphs, which we call parent functions, and move them to avoid tables of values. These translations are going to be a huge advantage to graphing because, again, it eliminates the need for that table of values. A translation of a graph is a shift in its location. It literally picks it up and puts it down somewhere else. Every point is moved the same distance and same direction. The function that you see here is the one we're going to use for all of our parent functions, f of x minus h plus k. The number at the end we refer to as k will be added or subtracted. If it's a positive number that's been added on the end, that'll shift the graph up k units. If it's subtracted at the end, or a negative number, it'll shift it down that many units. H is a little bit more complex. It's with the x variable. Usually it's going to be in parentheses, but it's always with the x. If it's x minus an h number, that's going to shift it to the right that many units, and x plus an h value will shift it to the left h units. And finally, there's one extra piece we'll get to, and that's if there's a negative sign in front of the entire function. This reflects it about the x-axis, almost like a mirror. It'll flip the entire graph upside down. So this isn't exactly a translation, but it is a shift in the graph itself. So we call this a reflection. All right, first example, or before we do that, this is a list of the 6 basic parent functions. I just copied this from a page in your book, from page 176. You'll want to use this. Every single problem that we do will be one of these 6 parent functions. You'll see on each one of these graphs, a point or several points are listed to help you know where to start. So before you do any of the examples, we're going to start by graphing a parent function and then shift it from there. The first example is x minus 2 quantity squared plus 1. If you go back to that list of parent functions that I gave you, you'll see that this is actually just a transformation of the graph y equals x squared. So if you're writing down this example, you should first of all go ahead and plot the y equals x squared graph. The 3 points you see here that I have labeled would be really good points to start with, actual dots on your graph. I also put some extra ones, the point 2,4, the point negative 2,4, and then 3,9, and negative 3,9, just to help me with the translation itself. So this one's first. All right, in this problem, h is actually equal to 2 because it's x minus 2. K is equal to 1. Now, according to translations, that means I'm going to shift to the right 2 units and up 1 unit. So right 2, up 1. Okay, let me show you what that looks like. I'm going to use color to do this, and I think it's a good idea if you do the same thing on your examples and your work. Maybe even like a pencil for the original and then a pen for the second graph. All right, so every single point that's going to happen, I'm going to move it to the right 2 and up 1. So I'll start with 0, 0. It moves to the right 2 and up 1. The point 1, 1 moves to the right 2 and up 1. This point negative 1, 1 moves to the right 2 and up 1. Right 2 and up 1. There's another point I moved. Right 2 and up 1, and I think for those very top points it's going to go off my grid, so I'm going to leave that go and then go ahead and connect the dots. This is the translated graph, and again it completely eliminated the need to make a table of values. This was enough information to get a good picture and some solid dots. All right, the next one is 1 over x minus 1 plus 1. Of the 6 parent functions on page 176, this one matches up to y equals 1 over x. The graph of 1 over x has 2 separate asymptotes. It has one on the x-axis and one on the y-axis. When you translate, those asymptotes will also move. So I want to identify exactly what the h and k values are for this one. Now you don't see parentheses on this problem, but they're there. We assume that anytime you have a denominator, there are parentheses in that denominator. So h is actually positive 1 down there. The number added at the end would be the k value. So this one's going to shift to the right 1 unit and up 1 unit. Okay, let me show you what that looks like. Every point, right 1, up 1. Right 1, up 1. Not only that, but the asymptotes themselves will move right and up. So the one you see here right in the middle on the y-axis will now be shifted over 1 unit. I'm going to notate that with a dashed line. It's not part of the graph, but it helps me know the boundary. The x-axis asymptote is going to move up 1. So now I have enough to connect and draw this line. I'm going to make sure it goes through that point that I drew and bends around the asymptote. All right, one more. In this one, y equals negative absolute value of x minus 2 plus 3. So this is the first time we've seen that negative out in front. The parent function from page 176 is y equals the absolute value of x. It's a V-shaped graph. There are 3 points that are nice to have on there, 0, 0, 1, 1, and negative 1, 1. Again, start by drawing this graph. One thing I noticed right away is that this thing is going to get reflected. Before, it really didn't matter if we went right, left, up, down, in what order. As long as you did those things, you ended up at the right place. Reflections actually have an order. They have to be done first. So because of that negative, I'm going to make sure all of these points get flipped upside down. Now 0, 0, if there's a mirror lying on the x-axis, isn't going to get flipped anywhere. But the other ones do. So now my graph looks like this. This is the opposite of the absolute value of x. Now let's look at the other parts. H is going to be positive 2. Always the opposite in there with the parentheses. And k is 3. So for this one, I'm going to move to the right 2 and up 3. So let me do that in a clean graph. Flipped it upside down. And let me use a different color just to show the next transformation. Every point now will move to the right 2 and up 3. Okay, there's the 3 points. And the purple graph that you see is now my final graph. So I'm showing each step along the way. The reflection is in blue. This one would actually represent y equals the opposite of the absolute value of x. And then the final grid is in purple. Y equals the opposite of the absolute value of x minus 2 plus 3. Again, color is really useful, or at least different styles of pen, pencil, just to show the original versus the new one that you've transformed.